the different models of supernova core collapse that we have. Okay, but let's get back to this. So how do we actually catch neutrinos? Well, they're electrically neutral, so it means that they don't undergo the types of interactions that most of the other particles do in our detectors that we utilize and we exploit those different types of mechanisms to actually see those other particles. The only way that we can get a neutrino to do something is basically if we have it hit a nucleus head-on, in which case we can infer that a neutrino has been there and has hit a nucleus by the stuff that comes out from that collision. And this doesn't happen very often, this direct hit of a neutrino with a nucleus. So what we usually need to do is to build very, very intense beams of neutrinos and use large, dense, super sensitive targets on which neutrinos can interact. And even so, we can actually only detect and study a small portion of the neutrinos in our detector. Most of the neutrinos will actually go through without doing anything. And we also have to run these experiments that we use to detect them for really, really long times, over long beam exposures, because it's really just a game of statistics, and we want to observe as many neutrino interactions as possible. So we need intense neutrino beams, big detectors that are dense and very sensitive, and patience, lots and lots of patience. And there's a reason why neutrinos interact so little. That's because they interact through something called the weak force. In the world that we live in, the majority of processes around us and interactions around us are actually mediated by the electromagnetic force. This is the force that keeps an atom together because it allows for the attraction between negatively charged electrons and positively charged nuclei, or a positively charged nucleus. And we also know that there's another force, the strong force, and that's responsible for keeping the nucleus together because it's made up of many like-charged particles, like protons. Neutrinos themselves interact through neither of these two forces. They interact only through the weak force, and this force is responsible for nuclear decays. For example, here's a neutron to a proton, an electron, and an electron antineutrino. And you see that the relative interaction strength for these three fundamental forces varies widely. In particular, the weak force is something like 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 12, 10 to the 12 weaker. The strength of it is 10 to the 12 weaker than the electromagnetic one. This strength can be thought of as the probability of something happening, the probability of having an interaction. Because of the nature of this weak force, which is the only force that neutrinos experience, that's why neutrinos are so hard to detect. So let's look at this neutron decay a little bit more closely. What's happening is that a neutron decays into a proton, and a neutron is more massive than a proton. So the mass difference is basically free energy that can be used to produce an electron and an electron antineutrino. And there's even enough energy to give these a kick. Another way that we can actually rewrite this process is we can take this electron antineutrino and we can turn it into a neutrino and put it on this side of the interaction. What this represents is not a neutrino production, as in the previous case, but actually a neutrino detection. So in this case, we have a neutrino that hits a neutron. This is time moving in this direction. And out of this collision comes an electron and a proton. So an electron neutrino can interact with neutrons in atomic nuclei and produce an electron. And in a similar way, a muon neutrino will do this and produce a muon. And a tau neutrino will do the same thing and produce a tau. So this is actually how we see neutrinos. What we look for is taus and muons and electrons to be produced in our detectors. So we can actually see the neutrinos themselves. They're neutral, they go through most of the time, and every once in a while, one of them will have a head-on collision with a nucleus and produce either an electron or a muon or a tau. And so we infer that an electron neutrino interacted by the presence of an electron, and that a muon neutrino interacted by the presence of a muon. So that means that our detectors have to be really good at distinguishing electrons from muons. And we can build such detectors, and I'll show you an example of one of them in a little bit. And the way that these detectors work is by imaging the energy that these particles lose as they go through our detector material. Both the muon and the electron have negative charges. And so as they zip through the detector, they actually continually undergo tiny, tiny collisions with atomic electrons. That causes ionization, which means that the electrons get dissociated from their atoms, and those electrons are what we call ionization charge. Our detectors can actually image that ionization charge, and by imaging it, basically what we can map out is the energy lost by the particle as a function of its path through the detector. So a muon, typically, because it's much more massive than an electron, travels in straight paths and loses very little energy due to ionization. But an electron, which is represented by this shower-like object here of ionization, undergoes a lot of scattering and other reactions, which leads to this messy shower of more electrons and positrons and so on, until they eventually all slow down enough and they get dissipated in the material. So we actually use a lot of imaging techniques to tell these particles apart whenever we use these types of ionization imaging detectors.